Today's episode will be a special one because I will show you the device we will use for the Petrie Museum Scan Project. The device we will use to scan the Petrie core number 7 or pre-dynastic hardstone vases. This device is actually the FreeScan Combo Plus from Shining 3D, and I'm glad that they are sponsoring me with this device. And I will tell you and explain why we have chosen this very compact and versatile laser scanner, laser and infrared scanner. I will also talk about the different technologies exist today, like structured light, CT scanning, photogrammetry. I will talk about the technology behind these scanning processes, and I will also talk about the metrology. What do we want when we are talking about precision or accuracy or these aspects? I will show you this device and the entire process we will use in the Petrie Museum for scanning with a few 3D printed pre-dynastic hardstone vases, and I have an old Anubis statue which we're scanning to see how it's picking up the little details. So I will show these. And I will try to explain as much as I can for those who are only listening, but I highly recommend to check out the footage on YouTube or Spotify, because probably I'm not mistaken if I say that I'm the first one who's showing this technology in this context, how we can analyze ancient artifacts and how we can use it mainly for the vase scanning project. So let's jump in. This video was reviewed by engineers at Shining 3D to ensure the accuracy of the metrological information and the techniques demonstrated. Accuracy and precision are a bit overused today, in this topic at least. I'm referring to the phrases like hardstone precision vases, pre-dynastic precision vases, or very accurate manufacturing in ancient times or antiquity, etc. So I would love to introduce these definitions. What do they mean, and what do we mean when we referring to these things? Let's talk about accuracy. By definition, accuracy refers to how close the scanned measurements are to the true dimensions of the objects. It's about the correctness of the data captured. In archaeology, accuracy ensures that the digital models we create are true to the artifact's original size and shape. This is critical for analysis, documentation, and replication. If an ancient vase is 100 mm tall, a scanner with high accuracy will measure it very close to this actual dimension, perhaps within 20 micron or 0.02 mm for the FreeScan Combo Plus. Precision. Precision relates to the consistency of measurements. If you scan the same object multiple times, precision indicates how repeatable the results are. It's often quantified by the standard deviation of the measurements. Lower standard deviation means higher precision. Precision is crucial for ensuring that if multiple scans of the same artifact are needed, each scan will align well with the others, creating a reliable composite model. For example, when using a scanner like the FreeScan Combo Plus, if you scan a part of the vase multiple times, you want each scan to produce the same or very similar data points. Why both matter? For an archaeological application, both accuracy and precision are vital. Accuracy allows us to understand the exact dimensions and features of artifacts, while precision ensures that our subsequent scans or models of the same artifact can be trusted for consistency, especially in detailed comparisons or when creating replicas. High-end scanners like the FreeScan Combo Plus offer metrology-grade precision, meaning they are designed for measurements where every fraction of a millimeter is significant. This is achieved through advanced calibration process, high-quality sensors, and sophisticated algorithms. In applications like reverse engineering, for example, high accuracy and precision allow for reverse engineering of ancient technologies or art techniques. In quality control, for example, in modern manufacturing, these terms ensure parts are made to specifications. Or in research, the researchers can study degradation, wear, or intentional modifications with confidence in the data. So we can face very complex challenges when we want to have an accurate and precise scan of an artifact. For example, the surface characteristics. Like reflective or dark surfaces can challenge both accuracy and precision. Environmental factors like lighting conditions or temperature or humidity can affect the camera, the device, the calculation of the data points. These has to be controlled, or the device has to be calibrated to these conditions. But there's another factor which is important, the resolution. Resolution in 3D scanning refers to the level of detail that can be captured by the scanner. It's often described in terms of the smallest feature size that can be detected or the density of the points in the resulting point cloud or mesh. Resolution can be quantified in various ways, like point density. This is how many data points per unit area or volume are captured, basically. Higher density means more detail. Or it can be quantified in voxel size in CT scanning, the size of each 3D pixel or voxel in the reconstructed volume, where smaller voxels mean higher resolution. Or it can be quantified by the feature detection, which means the smallest size of the feature that can be accurately represented in the reconstructed 3D model. Why resolution matters? In a detailed study, high resolution allows for the study of fine details that might be invisible to the naked eye, or in lower resolution scans such as hieroglyphic inscriptions or tool marks on ancient objects. In digital preservation for digital archiving, high resolution scans ensure that all possible details are captured for future reference or study. Or we can also talk about resolution in reproduction. When creating replicas or 3D prints, resolution impacts how faithful the reproduction of the original. Here's a very, I think, self-explanatory graphic about how the accuracy and resolution is related. So higher resolution means more measurements and therefore more details. However, it's important to note that higher resolution does not mean higher accuracy. So the first on the left represents a small surface captured with correct surface location. It means it's captured with a high accuracy and high resolution. In the middle, small surface lost, but correct surface location is captured, so it's high accuracy with low resolution. All the data points are on the right location, but some of the data points from the original object are missing because they were not captured. When low accuracy and high resolution is present, then we have incorrect surface location, basically. It can be hard to understand the differences between resolution, precision, and accuracy. So accuracy is about how close the measurements are to the true value. Precision is about the repeatability of the measurement. And resolution is about how detailed those measurements can be. So high resolution does not inherently mean high accuracy and precision, although high-end scanners usually provide both. I've collected five significant technologies which basically exist today. Photogrammetry, structured light, infrared, laser, and CT scanning. I will show a comprehensive table comparing all of these technologies, but first I would like to talk about each of them in a little bit detailed version. So let's talk about the photogrammetry first. Basically, photogrammetry involves taking multiple photographs of an object from different angles, and they are using a software to stitch these photographs together. So you can imagine that an object is turned around on a turntable, and we can use one camera to take hundreds or thousands of photographs from every possible angle, and after the photos were taken, we will use a software to stitch these images together, calculating the depth and geometry to create a 3D model. The software will use edges, corners, and other textural features or surface imperfections to align these images. So when we are capturing multiple images from various viewpoints, and these can be taken with standard cameras, or we can use DSLR cameras or even smartphones. We can reach a very high level of accuracy if we are using very high-resolution photographs and state-of-the-art software. The software analyzes the images and it will find matching points or features across different photos, determining the position and orientation of the camera for each image. This data is used to triangulate the position of these points in a 3D space, basically. So the 3D reconstruction will use these points from the point cloud, which is then meshed and textured to create a 3D model, basically. There are a few pros and cons of this technology. So it's cost effective because it requires only a camera. Can scan both large and small objects, and indoors or outdoors, and you will also capture the texture and color of the object. The cons, it requires good light conditions. So because we are relying on the cameras, the camera has to see the object, and the process can be computationally quite intensive. Might not be as precise for small details or for small objects with repetitive patterns. Yeah, but it's very easy to use. So the next one on the list is structured light. Usually when we are talking about structured light, we can talk about white and blue light. So this white or blue light pattern is projected onto the object, and an advanced algorithm will calculate the point cloud data based on how the pattern is deformed on the object, because from the deformation it can calculate the distance, how distant this object is or this point is from the camera or the projector. Blue light offers a better precision and higher quality results because its wavelength can be filtered out more accurately than that of the white light, and enhancing resolution due to its characteristics. So blue light is a bit more better than the white light, and I think that's when you want to achieve higher accuracy, you usually use blue light. And there are pros and cons with this technology as well. So the pros are high accuracy. It can scan quite quickly. As we explained in our previous episode with Adam Young, he started the vase scanning project by analyzing the vases with a structured light scanner, which was basically a fixed box with a projector that was projecting the structured light on the object, and the object was turned around on a turntable. So this technology can achieve a very high level of accuracy, and we are talking about less than 20 microns, for example. Obviously, it depends on the device themselves, but it can achieve a higher level of accuracy than laser scanners, for example. What are the cons? It requires the object to be in direct view of both the projector and the cameras. Bright ambient light or reflective surfaces can interfere with this technology. So the cameras may not be able to determine the pattern accurately or the deformation when the surface is too reflective. Another version of this is the infrared structured light, basically. So similar to structured light, but it uses infrared patterns which are invisible to human eye. This can be useful in applications where visible light might interfere with the scanning process, and an infrared camera captures the deformation of the pattern. So we are projecting an infrared pattern and the camera is only capturing the infrared. So we cannot really interfere with other type of light sources, except if we are on the sun, because sun can inject infrared wavelength light, and that can cause any problems actually. The pros are that useful in environments where visible light might not be desired. It's also versatile in terms of material scanning, so it can capture textiles, different surfaces, different materials. The shiny ones are tricky. When I tried, I cannot really capture the shiny metal surfaces. It's just not possible. It's not picking up the surface. And it also can be combined with thermal imaging. Thermal imaging is also a very interesting part, but we are not working or using this technology right now, so it's not really relevant for us. The cons can be affected by ambient infrared sources like the sunlight and can be sensitive to temperature. And another con is, as I said, certain materials might reflect or absorb infrared light in ways that complicate the scanning process, like metal things like a metal cup which is polished. It won't pick it up. The next one is the laser scan. So the laser scans the surface and the sensors measure the return time or angle of the reflected light. So it can use either triangulation, which is basically, it means that it uses the angle of reflection to calculate distances. It's common with desktop scanners, laser scanners, or time of flight can be also used for calculation. When it's using this, it measures the time taken for laser light to travel to the target and back. So it's suitable also for long range scanning. It's very similar to the LiDAR. It's basically this, using or ejecting a laser beam, and it's measuring the time taken for the laser light to travel back to the sensor. And that's how it can, from a drone, as you could see in Graham Hancock's new series, Ancient Apocalypse 2, I think, on Netflix, how they scanned the South American rainforests with laser beams or LiDAR. The pros with the laser scanning is that it can achieve high accuracy and robust in a wide range of lighting conditions. So it doesn't really matter if it's dark, if it's sunlight, you just have to calibrate it when the light condition's changing, you have to calibrate it in that new condition, and then you are good to go. The cons: direct exposure to laser beams can be harmful in most scanners except the Shining 3D scanners. So in the FreeScan Combo Plus, the lasers are eye safe, so it's not a problem here. Lower speed usually is also a con for laser scanners. FreeScan Combo Plus is solving this issue with 50 laser lines. So it's projecting 50 laser lines at the same time, and it's speeding up this entire capturing process. I will show you, it's quite effective. Another problem can be the surface reflection. So when it's a highly reflective or transparent object, it can be problematic to scan. So when I tried to scan a Guinness pint, glass pint, this was not possible because the laser beams were just passing through the material and not reflected. So it cannot measure it. And another con basically with laser scanners that it's not capturing a color or direct texture. If it has a surface deviation or something, obviously it will be captured, but it's not capturing the color. And with pre-dynastic vases, not like this one because it's a double color print, but with very nice granite vases, it's a little bit pity that we cannot capture the color information because they are just beautiful. So, but there are other types of scanners which could capture the color. So we have to it's a trade-off between texture and accuracy. So if you want a high accuracy, you will lose the texture or color information. So the last type is CT scanning. CT scanning, or you can say X-ray computed tomography, is a medical imaging technique adapted for industrial, scientific, and even archaeological uses. It produces 3D images of internal structures of objects by reconstructing multiple X-ray images taken from different angles. So this object is placed on a rotating platform, or it can be inside the scanning ring also, where an X-ray source and detectors are positioned opposite to each other, As the object rotates, the X-rays pass through it, and the attenuated X-rays are detected on the other side. So X-rays coming through here, detectors are here, and the attenuation is measured by the detectors, and this process is repeated at many angles, hundreds to thousands of views, and each set of X-ray measurements creates a projection image which represents the density of materials the X-rays have passed through. So we can differentiate on the scan between the different materials in the object. Using algorithms like filtered back projection or iterative reconstruction, these 3D projections are computationally combined to create a 3D volume representation. This volume can be sliced into any plane for viewing or rendered into 3D model, as you wish. And the good thing that, the pros, that this is a non-destructive technology. It can achieve a very high level of resolution on microns, so a few microns even, and also it can differentiate materials. There are a few cons with this technology because it's very expensive, comes with a radiation concern, so you need a big room with appropriate protection. It produces large files and it's time consuming to filter and analyze these large files. We also talked about these CT scanning analysis problems with Adam Young in the previous episode, because he told me when he captured objects like this with a CT scanner, inside of the vase was very noisy because in the wall, in the material, there were different. It's a composite, it's not a homogeneous material, it's a composite material. It was reflecting and modifying the X-rays, path of the X-rays in a different way. And when the X-rays were passing through, depends on which material they hit, they could generate noise in the interior of the vase. And it's very hard to filter it out because you don't want to remove data, you don't want to remove part of the wall, but you want to remove the noise. But it's very hard to decide which one is the part of the wall and which one is the noise itself. So that's why for interior measurements, for the vase, for the accuracy and with the methodology we want to use, it was not very useful and effective. Outside is perfectly captured, but when we want to see the wall thickness, for example, the wall thickness deviation, it was hard to decide what to filter and what not to. This was one con of the CT scans. Otherwise, it's the highest accuracy we can do, but unfortunately we cannot bring it into a museum, for example, because not only the files it produces large, but it's the entire machine is also large. We cannot. The Petrie Museum, for example, is very small. We couldn't bring it in. There would be no room for this kind of equipment there. And also the object size is limited to the scanner's rotating platform size. So when it's put in to the machine, some platform had to hold it and rotate it, and the object size is limited by that. So our choice was the FreeScan Combo Plus from Shining 3D, mainly because its versatility, compact and portable design and accuracy. This amazing instrument has an innovative combo light source equipped with blue lasers and an infrared vertical cavity surface emitting laser for markerless scanning. The product is extremely compact and portable, weighing 620 grams. Thanks to its innovative combination of intelligent cameras and light sources, it's applicable to diverse industrial 3D scanning scenarios. It's perfect for narrow scanning due to its small camera angle, and the new 50 laser line edition enables fast scanning, capturing 3.6 million points per second. It's an amazing choice for quality control applications, offering an accuracy up to 20 microns. Additionally, it can capture fine details with a resolution up to 50 microns using 7 laser lines and deep holes with a single laser line. Where markers are not applicable, the infrared mode can be used to unlock more possibilities. I would like to thank Shining 3D for the collaboration and the support that they let us to use this incredible device. And actually, if you are interested in their wide range of devices, they have metrology grade scanners for smaller and bigger objects. They have not metrology grade, but desktop scanners. They have dental scanners. They have a lot of incredible things. And you can check out their wide range of devices on their website, and you can find that link below in the description. And we hope that we can try out more and different devices from Shining 3D for our archaeological research at Artifact Foundation, because we have other plans like site scanning, scanning statues, scanning boxes, scanning different things. It would be interesting to see how their instruments can be used on site in Egypt. This size and weight is crucial because it comes in a smaller suitcase, a very tiny suitcase, and you can bring it on the plane with yourself. You don't have to check in this very expensive device. You don't have to check it in. You can put it in a hold-on luggage. It's just easy to travel with. And it's very important that a lot of the museums have limited space. For example, the Petrie Museum had very limited space. We couldn't set up a much bigger scanning device there, like a stationary structured light scanner. And also when we're going to site to scan a statue, scan something, it's much easier to just bring the laptop and this one. And we don't have to set up the big stationary stands and the projectors and all these things. So it's very important when you are in a field or when you are in a tiny museum that your device is portable. We are planning on site scanning, so we would love to support archaeologists on the field to scan their findings, even with another scanner which can capture the texture, so we can archive and capture the entire wall sections basically of a tomb where it's intricately carved or painted or both. And it's also important to mention that 20 micron or 0.02 millimeter is the higher end in terms of accuracy for handheld portable scanners in 2024. So I'm very grateful that we could use a state-of-the-art scanner actually for the Petrie Museum project. Thank you, Shining 3D. Hi everyone, thanks for tuning in. If you are enjoying the show and want to support me, there are a few ways you can help. By becoming a Patreon member, you will get access to Discord, exclusive content, and behind-the-scenes updates on my research. For instance, I recently traveled to London to scan pre-dynastic vases at the Petrie Museum. Your support makes that possible. Just search for Ancient Technology on Patreon or check the links in the description for all donation options. Your support not only keeps the podcast going, but also funds the research behind it, covering costs like equipment and travel. Thanks again for being here, and I'm excited to keep bringing you more great content and discoveries. But now, let's jump back to the show. So after talking a lot about this device, let's see how it performs, and let's scan some pre-dynastic vases. So let's start the scanning. But the first step, or the step 0 basically, is to calibrate the device. This is a precious calibration board which we have to take care of. Handle it very carefully, not scratch it, not break it, etc. So we will use this calibration board for calibrating the scanner before every session in the museum. Because when the lighting condition changes, so we have different lights, different light sources, different setup, we have to recalibrate to make sure that we are using the best of the device. So the calibration is a guided calibration. What we usually do is to plug it in, let it warm up to roughly 30 degrees of Celsius, and then we start the calibration. So basically we can just click on calibrate and it will guide us. Too far, pull down, so we have to go closer and up, We have to try it from a few different angles. But the graphics on the right side is always telling you which position you should keep the scanner in. Yes, and that's all. So technically, once the calibration is finished, it's recommended to store the plate carefully to avoid scratches or damage to the plate. Yes, we will store it carefully. After the calibration, we can start the scanning basically. We have this turntable with the markers all around in a random position. It's very important that the markers have to be placed randomly, because symmetry can trick the scanner. We don't want that. So basically this is the primary plane for tracking. And we will start with this spinner vase. It's also a pre-dynastic hardstone vase, or at least a 3D print of it. And I have created some accessories to scan properly. The scanner has to see 4 markers at a time to be able to track them. So it's tracking the markers, and that's how it knows where it's oriented in the 3-dimensional space. For example, these curved bottom objects are not stable on the plate. So when I'm turning the turntable, they can move. And that's not very useful, because they have to stay steady according to the markers or compared to the markers. So that's why I created these rubberized bays where I can also place a few markers. This doesn't have to be in the center. It's not important. The important thing that this should not move on the table compared to the markers basically. So I put it on this one. It doesn't matter if it's centered, aligned perfectly, no one cares. And by turning this, you will see when I'm capturing, by turning the table, the scanner will track the position with the markers, and it will capture the surfaces and details of the vase. But if I'm scanning the bottom side, it cannot see the markers. It cannot see the markers if I'm not using this stand. So that's why I created this stand. So this way it won't see the markers in this angle. That's why I have created a stand which elevates the entire vase a little bit. And in this case, even if it's tilted in this angle, it will see some markers on the stand. I have also created these dices to enhance this marker visibility further. It's attached magnetically to the turntable, so we can place them all around, try to place them randomly as possible, all around the object. And by turning the object, you will see that the markers will be probably visible from all possible angles. But first, we have to scan the global markers, create a global marker file, and after that we can put several different objects on the same marker setup and scan them without the need to scan the markers again and again and again. It's just basically speeding up the entire process. So here, after calibration, we can select between laser mode and infrared mode. First, I will show you the laser mode. For the infrared mode, we don't need the markers. We can use markers, but we don't need them. For the laser mode, we need markers. So I will create a new project group. And I will scan the global markers. As you can see, it's zoomed in to the picture quite well. But in this window, here in the camera window, you can see what the cameras are actually seeing. So if I turn it around, it's detecting the markers and highlighting the currently tracked markers with red. So I will turn this around several times, try to move it around so it can see all the markers, because these markers will be very useful for the tracking. It's a quite fast process, but we don't want to do them too many times because it's still time consuming. And for example, in a museum setup, we don't have infinite amount of time. So we have to do it as quickly as possible. And after scanning the markers, we can check if it's correct. Yeah, seems fine. Usually what I do is I highlight all of them and I create a plane so it will only collect data above the plane. Otherwise, the entire turntable will be also captured, and we don't want to do that because it's more resources, it uses more resources and more memory. So we don't want to use more memory. We can capture the stand. Actually, it's not a problem, but we don't want to capture the turntable and what's around the turntable basically. So this way we will basically create a cutting plane, and we have 104 markers in total and 39 are selected from those to create the plane. And this software will basically create a plane, fit a plane on these red markers, and we don't need an offset from this, we just need plane. There's a global marker optimization which is useful for the software itself, and after the optimization we can basically export the scan. So after we scan the markers, we can save it to a global marker file and also save it with the plane. And next time we can just load it. We don't touch the markers, just load it next time. We can start to scan the object immediately after we just loading this global marker file. But you will see. Now we can start to scan the mesh. So I place this on the plane. Yeah, I try to place it nicely, but it's fine. So after we put it on, we can select the resolution we want to use. I will use 0.1 millimeter. It's enough currently for demonstration. We don't need much higher resolution because it just needs more RAM and time. We can press on confirm, and we can select between the laser light source mode, and the more the faster basically. So I will select 50 lines, and if I want to capture something from the interior, from the inside, there is a feature with one line that's perfect for deep hole capturing. It won't capture the complete interior, but it will capture some from the bottom. And we can select between normal and reflective objects. It's not really reflective, so I will stay with the normal one and set the auto exposure. It will adjust the camera's exposure automatically. It will start to increase the light intensity of the laser beams and then set it the best based on the current light situation and conditions. So yeah, I can start. I can just press this little button here, or I can go here with the start scan play button, and it will start with the auto exposure. I have to stay steady. It will adjust the lights, and when it's ready, it's already capturing. It's already capturing the vase. It's perfect. When it's green, I'm in the gray distance. When it's red, it's too close, and when it's blue, it's too far. So I will just stay green and turn it around until it's capturing a nice level of details. Actually, I can see where it's still yellowish. Those are the parts with not enough data points. Data points are collected there, but based on the resolution settings, it seems not enough. So that's how I can know actually where I need to capture more points. I have to move it around to do the triangulation, and I can actually try to go inside with the laser beams or the lines, but it's not going to capture much, I'm afraid, because the neck is quite narrow. I can try to come back with the one line mode, and now if I'm turning it around, it can still see some of the markers because I have markers on the stand. The red markers are the currently tracked and detected ones. So that's why I needed them. Otherwise, the markers on the plane, on the table, they are not detected at all, or not tracked currently. So I need to go around slowly and move it a bit until it's detected. Yeah, some noise is created. I don't know the correct explanation for the noise all around the object, but the object is captured quite nicely. And later on we can delete these floating points, which are not connected to the object directly. I will try to go around the neck a little bit more, but here I'm just demonstrating. I'm not trying to scan it perfectly because that's quite time consuming and that's not our target right now. Can pause the scan with the same button and wait a bit for the software to calculate its own thing. Yeah, I have some noise, but these are just not connected parts. The base basically is nicely captured. I can see the 3D printing imperfections. I can see here also this dents, the seam position of the 3D printing slicer setting. Yeah, it's quite nice. And this is only 0.1 millimeter. We can go down till 0.05. This is fine. I will open a new project, and with the new project, I will scan the bottom. I will scan the bottom of the vase, I cannot change the resolution at this point. I will just, I can open the saved global marker file. It will load the plane and the markers, and I can go on scanning mesh, and let's see, setting the exposure again. And we just turn it around. And it's capturing nicely, filling up the holes. I can see already these imperfections in the print, these little dents and imperfect areas, even the lines of the filament. I will go for the lock handles. Yes. And the lock handles are helpful here because after I scanned both the top and bottom part, in this software I can go and align them together. In our research, we don't really do that. We don't really want to align these two scans because we are not sure what kind of error or what magnitude of error will those alignments bring in, but we can analyze the parts separately, so it's not really important to align them. We can align them for 3D printing for sure, that's useful, but for the proper micron level analysis we don't want to align them. Okay, so I consider it fine for now. And so after we scan both parts, we have it in the same project and basically two different files. I want to get rid of the unnecessary parts or unwanted parts. So let's see the first scan. I can go on the vase, highlight a section and say to connect domain. It will find all the domains connected to this part, which means that all the vase body part. And I want to keep this, so I will invert the selection. So basically select everything else and delete them. Maybe it needs some time for processing the point cloud, but it will delete the not necessary parts. And then I will go for the second scan and do the same thing. So we have both vases and we can go for the alignment. There is a built-in alignment feature, so we can select both project parts. Yes, and we have to, sometimes we have to tell the software where to look for the alignment features. Auto feature alignment, let's see what's happening. Well, it couldn't find, so we have to scan enough details from both sides to be able to align them. But don't worry, we have a few of these details, we just have to look for them. So I can manually pinpoint features for alignment. So here we have one feature, which is, I think, this one here. And here, and let's say this is a distinct feature. And now we can apply. But when it's not too symmetrical, it's easier for the software to find those features where it can be aligned. But voila, here we go. This is our aligned vase, and we can go next, can exit it, and as you can see, it's aligned. And if you want to print it, we can also optimize the scan for printing. So we can do a standard optimization, smooth it out in not so highly, but in medium setting, with medium settings. Remove spikes. Let's see. Remove small floating parts to an extent, and we can also maximize the triangles. Let's do that. So it's a little bit smoother. As I can see, there are still a bit spikes all around. I don't really experiment with this optimization so far because we don't really need it. We don't want to remove data points. Okay, we can go confirm and save it and play with it further. Or we can go back and scan another object. So when we want to use the infrared mode, we don't really need the markers. We can use them, but we don't need them. So I will scan these pre-dynastic hard stone vase, this other one, the OG vase, and I will select the ER mode in the main menu. I will create a new project group. Here we can select between portrait and object, so we can actually scan someone else if we want. It's quite cool. It's a cool feature. I will select the object, medium and large size, and in the select mode of alignment section, we can select between features and global marker alignment or hybrid. So the feature alignment will look for the geometrical features of the object, edges, corners, etc. But it can also use the markers, and it can use both. That's the hybrid for. That's what the hybrid is. And I will select the lowest resolution, or the highest resolution possible, the lowest value, 0.2 millimeters, and apply. We can leave every settings here as default, and we can just click or press the start button, and we can check the camera window. We can zoom in a little bit, and we can see the yellow parts. The yellow parts are the sections or areas where not enough data point captured yet, so we need to wait until it turns blue so we can move forward. And ideally we want a full blue object at the end, so no yellow parts, no partially captured parts. Full blue is the ideal. So I will go around the vase just slowly. It's already capturing quite amount of details. I will just move it slowly, and I can check here how good is my distance from the object. So when it's, the ideal is green, and I would like to keep that one. It's also visible there on the left side of the user interface. Yes, I have to move it a little bit down so it can capture the base and the under the lip, but somehow the tracking is lost, so I will move back where the handle is, so it can keep the tracking, and I will turn it sideways. And I will try to capture these parts. Yes, seems like fine. It's relatively fast, as I mentioned at the beginning, but the tracking is not always easy. So something from the neck, and I think we are kind of ready. Just press the button again, it will pause the scan. Yeah, there is a misaligned something there. So from here we can just select the vase and invert the selection. Do something similar like with the laser scanning results. I will delete the unnecessary data and I will select some parts of the vase, connect the domain, and this way we can, if we invert the selection, we can remove the floating parts. We can apply the edit and we can click on generate point cloud. So this is needed for the mesh. Go to the mesh model, and here we can select the semi-watertight. It will fill the larger holes, not the bottom and the top. For those, to close them appropriately, we need to do something else, probably in Mesh Mixer or other software, and also to create a certain wall thickness we need to use another software probably. We can optimize it medium, remove small floating parts. We can increase this value a bit and remove spikes, fill small holes. Yeah, let's see. So this is the mesh solid object. Yeah, the lock handle holes are filled. Yeah, there are so many settings that I don't want to show all of them, but now you have an idea what's possible and what's not. I will go back to the scanning mode, and if we have a taller object like this statue, this Anubi statue here, if we have a taller object, maybe the dices are not enough, even the stand. Probably we will need to use a higher version of these dices, same dice basically. So I want to show you how to use the taller version of the markers. There is a feature called partial HD scanning, which allow us to scan an object with a lower resolution and go back on some parts, for example on this necklace or pendant, and scan only that region with a higher resolution. That's very interesting. I will show that. But first we have to set up the markers. So we have these 3 taller markers, and for example I want to place the statue here. I can attach these higher markers to the table with a magnet and dices as well. I still want to be random with the markers, so okay. I will select laser mode. I will create a new project. We can basically start scan the global markers. Using the camera window is quite useful because we can see what the camera can see. I just want to use the turntable markers for the plane. So cutting plane, create plane, apply, do some marker optimization, After this, we are good to go. We can place our precious object on the turntable. So I will scan the mesh with a relatively low resolution, 0.5 millimeter, to show you the partial HD afterwards. So I will select 50 lines, normal object and auto exposure. Yes, and I can start scanning. You can see the camera window. We can see the exposure process or the auto exposure settings in the camera window. And it's already capturing. So I will capture the entire object because it's not a very high resolution. Okay, it's not really necessary because we don't want to go for the full scan. So after I have this scan, I can go here on this pendant or necklace or whatever and select partial HD scanning mode. I will go down to 0.05 millimeter. And let's see what's happening there. I have to select an area. I want to scan this area. This area will be deleted. It also notifies you that selected HD scanning area data will be deleted and cannot be restored. Would you like to proceed? Yes. Yes, and after it's deleted, I can rescan that part. I can zoom on in and you can see how it's recapturing basically this part. I can move it around a bit so it can also capture the side walls. And it takes a lot of time actually. It takes a lot of time, and you can go down to 0.01 millimeter if you like. You can scan it down to that level. Yes, and as you can see, it's filling up this void, this space between this. Basically, it's filling up the holes. Yep. So here we can see the new resolution, the 0.05 millimeter here in the partial HD mode. You can clearly see how different it is from the original resolution. It's amazing. So this was it for today. I hope now you will better understand when we are talking about accuracy, precision and resolution. And I hope I could introduce these technology so you will understand the upcoming results, because I promise the results from the Petrie Museum will be dope. And I would like to thank Shining 3D again for supporting me with this device, and I'm very happy that we could use cutting-edge technology for our research. If you like my work and the videos I make and episodes, and if you want to support my research, please consider subscribing to my YouTube channel or joining me on Patreon, where you can have extra perks like behind the scene footage or early access to the new research results and videos. And actually only 6% of the viewers are generally subscribed to my channel, so please keep subscribing and see you next time. A massive thank you to my incredible supporters: Artango, Oannes, Sarah Cox and Basana. Your generosity fuels this journey into ancient technology, keeping this show alive and pushing my research further than ever. As the ancient Egyptians would say, Ankh Veja Seneb.